dear students. In the previous session, we derived an expression for lens maker's formula, that is 1 by f is equal to n21 minus 1 into 1 by r1 minus 1 by r2. Here f is the focal length, n21 is the refractive index of second medium with respect to first medium, r1 is the radius of curvature on first surface, r2 is the radius of curvature of second surface, spherical surface. We can also write this formula as 1 by f is equal to n21 by n21 is n2 by n1 minus 1 by r1 minus 1 by r2. Where n1 is the refractive index of first medium, n2 is the refractive index of second medium. Suppose if refractive index of the n1 is the refractive index of surrounding medium and n2 is the refractive index of the lens. So if the surrounding medium is A, then n1 is equal to Na, refractive index of A. The refractive value of refractive index of A is 1. So this formula becomes 1 by f is equal to n2 by n1 minus 1. Sorry, if n1 is equal to 1, then the formula becomes n2 minus 1. That can be generally written as n minus 1. n2 can be written as n. If n1 is equal to n is equal to 1, then n2 is equal to n. So n minus 1 into 1 by r1 minus 1 by r2. Okay. Next, write the formula for lens. Write the lens formula, that is for thin lenses. So thin lenses are the lenses whose thickness is negligible as compared to radius of curvature. So thin lenses are the lenses whose thickness is negligible compared to the radius of curvature. So the lens formula is given by 1 by f is equal to 1 by b minus 1 by u. This is the lens formula for thin lenses. That is lens formula. Here 1 by f is the focal length, b is the object and u is the image distance. b is the object distance, image distance, and u is the object distance. So this is the relation which connects focal length, image distance and also object distance. Okay. Linear magnification for lenses, thin lenses. Linear magnification. It is noted by M. So this linear magnification is the ratio of height of image to the height of object, or it can also be defined as ratio of image distance to the object distance. It can be written as hi by ho or b by u. That is ratio of height of image to the height of object or ratio of image distance to the object distance. Okay. So this is the linear magnification. If the image formed is virtual and erect. If M is positive, real image formed is virtual and erect. If M is negative, then image formed by the lens is real and inverted. Is real and inverted. Shall I repeat again? That is M is positive, then the image formed is virtual and erect. If M is negative, then the image formed is real and inverted. Next, power of a lens. Power of a lens. This power of a lens is the ability of a lens to converge or how much it converts or diverges a beam of light. That is, this power of lens is defined as the ratio of focal length. Sorry, power of a lens is the reciprocal of focal length. Power is defined as reciprocal of focal length and is diopter. And symbolically it is represented by D, that is diopter. So now we define one diopter, that is diopter. If power is said to be 1 diopter, if f is equal to 1 meter. The focal length of the mirror lens is 1 meter, then power is 1 diopter. That is T is equal to 1 over f is 1 that is equal to 1. So if focal length of the lens is 1 meter, then power is said to be 1 diopter. Okay. Next, now we derive the relation between this power of lens and focal length. For that, let's draw a convex lens. Okay. This is the convex lens and this one is the principal axis for that convex lens. So this is the optical center. Okay. So let a parallel ray of light incident on this convex lens. What happens? It gets refracted. After refraction, it is focused at a point F. So this is the refracted ray. So in the absence of this lens, this incident ray is moving along this direction. In the absence of this glass, that means lens, this incident ray moves along this direction. That means it makes the incident ray direction makes an angle delta along with the refracted ray. That is the angle delta. It is the angle between the direction of incident ray and that refracted ray. So if this angle is delta, then this angle is also delta. The incident ray is incident at a height of h. So here it is this side is h and this is the focal length, that is f. Okay. So from the triangle, from this triangle, tangent of delta is equal to, what is tan theta? Tan theta is opposite by adjacent side. So opposite side is h and this is h. So adjacent side is f. So tan delta is equal to h by f. This tan delta is approximately equal to delta because here delta is very small. If theta is very small, then tan theta is approximately equal to theta. So delta is very small, then tan delta is approximately equal to delta. So this equation becomes delta is equal to h by f. And suppose the incident ray is incident at a height of 1 meter, that is h is equal to 1 meter. Then this equation becomes delta is equal to 1 by f. Okay. So this delta is approximately equal to power of the lens. So that will be equal to P is equal to 1 by f. So this is the relation between the power and focal length. So power is the reciprocal of focal length, and this power can also be defined as tangent of angle by which the ray of light converges or diverges at a height of 1 meter from the principal axis. Okay. Next we shall derive an expression for equivalent focal length of the thin lenses in contact. What is thin lens? Thin lens is a lens whose thickness is negligible as compared to its radius. So equivalent focal length of two thin lenses which are in contact. So equivalent focal length is the effective focal length which produces the same effect as that of the combined lens. Okay. For that, let's draw two thin lenses. Let's draw two thin lenses which are in contact. Like this. Two thin lenses which are in contact like this. They are contact like this. Okay. So this is the common principal axis for both the lenses. So let us call this first thin lens as A and the second thin lens as D. Now an object O is placed here. So this is the object O. A ray of light incident on this first lens, that is A. When a ray of light entering into this first lens A, so this is the incident ray. So this is the optical center and this one is the incident ray. After incidence, it gets refracted. But in this case, we assume that this second lens, in the absence of this second lens, this incident ray gets refracted like this. In the absence of second lens, this incident ray gets refracted along this direction. Okay, so the image of an object formed at this point. Okay, let us consider one more ray which is incident along the principal axis and which is incident on the optic center. So the ray which is incident on the optic, the ray which passes through the principal axis which passes undeviated, and these two refracted rays are meet at a point. So image of an object O is formed at this place, that is known as I1. So I1 is the real image of the object O in the absence of second lens. Okay. Suppose if second lens is present, so for the second lens, this I1 act as virtual object. For the second lens, this I1 itself act as virtual object for this second lens. So for the second lens, the image of an object is produced here somewhere here. So this is the image produced by the object with the second lens, that is I. Okay. So this is the object distance U. That is the distance between the optic center and the object, that is object distance U. So this I1 is the image distance for the first lens. I1 is the image I1 is the image formed by the first lens. So this is called as V1. So image distance for V1 is the image distance for I1. So let us call this image, real image, as I. So that is image formed by the second lens due to the virtual object I1. So this image distance is written as V. Okay. So this is the ray diagram. We know the lens formula for this thin lens, that is 1 by F is equal to 1 by V minus 1 by U. Call this as equation 1. That is the lens formula for thin lens. Here F is the focal length, V is the image distance, and U is the object distance. Now we apply this lens formula for both the lenses. For first we consider first case 1. In case 1, object O is the, in case 1, O is the object and I1 is the, in case 1, that is in the absence of second lens, O is the object, I1 is the real image of the object O. Okay, and U is the object distance. U is the object distance and V1 is the image distance. V1 is the image distance and focal length of this first focal length can be written as F1 and focal length of second focal length can be written as F2. So F1 is the focal length of A, that is first convex lens. So in case 1, O is the object. So this in the absence of the second lens B, it gets refracted, the incident ray gets refracted and forms the image at I1. So in the case 1, in the case 1, object distance U is equal to U and image distance B is equal to V1. V is equal to V1 and focal length F is equal to F1. For A, F is equal to F1. F is equal to F1. This is for lens A. This is for lens A. Okay. So now we substitute this in equation 1. You will get, instead of F, we will write F1. So 1 by F1 because equation 1 becomes 1 by F1 is equal to 1 by V. Instead of V, we will write V1. So 1 by V1 minus 1 by U. U is same. So 1 by U. Call this as equation number 2. Again we apply the same lens formula, thin lens formula for the second surface, the second lens, that is B. For second case for lens B. Second case for lens B. For the lens B, this I1 act as virtual object. I1 act as virtual object. So I1 is the virtual object object distance is this, that is V1. That is U is equal to V1. And image is formed at I, that means image distance is V. So V is equal to V. And focal length for second lens is F2. So we put U is equal to V1, V is equal to V, and F is equal to F2. In equation 1, you will get 1 by F and written as F2 is equal to 1 by V is written as same minus 1 by U. Instead of U, write V1. So 1 by V1. Call this as equation number 3. Okay. Now adding equation 2 and 3. Adding 2 and 3 equation 2 and 3. You will get 1 by F1. First we add left hand side. That is 1 by F1 plus 1 by F2 is equal to right hand side. That is 1 by V1 minus 1 by U plus 1 by V minus 1 by V1. Here 1 by V1, 1 by V1 get cancelled. Remaining is 1 by F1 plus 1 by F2 is equal to 1 by V minus 1 by U. We call this as equation number 4. Now comparing equation 1 with equation 4, we get 1 by V minus 1 by U can be written as 1 by F. So 1 by F1 plus 1 by F2 from it was equal to, from equation 1, 1 by V minus 1 by U can be written as 1 by F. So 1 by F is equal to 1 by F1 plus 1 by F2. 1 by F1 is 1 by F is equal to 1 by F1 plus 1 by F2. This is the effective focal length or equivalent focal length of two thin lenses which are in contact. That is 1 by F is equal to 1 by F1 plus 1 by F2. This is the formula for effective focal length, effective focal length. If n number of lenses are connected, then this formula can be written as 1 by F is equal to 1 by F1 plus 1 by F2 plus 1 by F3 etc. plus 1 by F1. Okay. This formula can be written in terms of power as 1 by F is reciprocal of focal in this power. So 1 by F1 can be written as P1, 1 by F2 can be written as P2, 1 by F3 can be written as P3 plus etc. up to Pn. That is effective power of the lens. Equivalent power of the lens is the sum of power of individual lenses which are in contact. That is P is equal to P1 plus P2 plus P3 etc. up to Pn. So the effective focal length for n number of lenses is given by 1 by F is equal to 1 by F1 plus 1 by F2 plus 1 by F3 etc. up to 1 by Fn. Similarly, effective power is given by P is equal to P1 plus P2 plus P3 plus etc. up to Pn, and also the effective magnification of the lenses, combined lenses is given by M is equal to M1 into M2. If the two lenses are in contact, then their effective magnification power is M is equal to M1 into M2, where M1 is the magnification of first lens and M2 is the magnification of second lens. If n number of lenses are in contact, then total magnification is given by M is equal to M1 into M2 into M3 etc. up to M9. Okay. So this effective combination is used in the manufacture of some cameras, telescope, microscope etc. In the manufacture of telescope, microscope and some cameras. Okay.